G'day and welcome to the next video in this linear function series. Today we're having a look at how to solve simultaneous equations graphically. So when we consider two or more equations, we can actually seek to find where they intersect, that is where they cross or where they touch one another. And this method is called solving simultaneous equations. Now if they intersect, basically we want to know the coordinates of that point where they cross, i.e. what's the x value and what's the y value. So using graphs, this is really easy. We simply need to just read off the point. I tell the marker, or whoever's looking at it, what the x coordinate is and what that y coordinate is. Sometimes in the question, you may actually be asked to sketch those lines first. And if you're not sure how to do that, I really encourage you to just go back and have a look at some of my earlier videos where we talk about how to sketch linear functions. So let's have a look at some examples here. Let's have a look at the first one. Solve simultaneously y equals x minus 2 and y equals minus x on 2 plus 4 using the graphs below. Okay, so you can see from the Cartesian plane there, we have these two lines and quite clearly they intersect. And so for us to solve it simultaneously, we want to know what this point is right here where they cross. And so it's as simple as working out, well, what's my x value and what's my y value? So my solution to this is simply x equals 4 and y equals 2. If you wanted to know what that coordinate was, you could just tell them that it was the point 4, 2. But as I said, when we're solving simultaneously, we want to give that x value and that y value. That's what they're asking for. Let's have a look at another one. Determine whether the point 3 minus 2 is the point of intersection of these lines. Now, if a point is going to be the point of intersection, it obviously has to lie on both lines. If the point lies on both lines, quite clearly, both those lines are passing through that point, and that must be the point of intersection. So we just simply substitute it in, and we're going to check. So we're going to see here, we'll say at x equals 3, y here equals 3 times 3 minus 11, which equals 9 minus 11, which is minus 2, which is exactly what I was going for. So happy days, that therefore lies on the line. Let's have a look at this one. At x equals 3, y equals minus 3 plus 4, which is 1. Uh-oh, bad news. That doesn't equal minus 2. So therefore we can say it's not the point of intersection. Therefore 3 minus 2 is not the point of intersection, as it clearly doesn't lie on that second line, is not the point of intersection, as it doesn't lie on y equals minus x plus 4. It's always good to give an answer. Don't just say no or whatnot. Actually write out a reason. That's what people want to see. All right, this last one here. Solve simultaneously the equations y equals 2x plus 3 and y equals 2x minus 7. Now just looking at both those equations and thinking about what is going on. So hopefully you're understanding there's a few significant features of any linear function. One is that it has a constant gradient, and what you notice in both of these, they both have the same gradient. Gradient, or m, equals 2 for both lines. And what do we know? If two lines have an equal gradient, therefore they are parallel. So we can say equal gradients, therefore lines are parallel. Okay, and what does that mean? There is no solution to this simultaneous equation. Therefore, we can say no real solution. And it's funny that that actually is the solution. In maths, we're right. There's no real solution. There's no points at all where those lines intersect one another. If you wanted to know what it looked from a graphical perspective, you could sketch those first, but it's obviously going to take you a bit longer. If I just drew them out really quickly, really rough right here, I've got a gradient 2 and a y-intercept of 3, so that's going to look something like that. Okay, and this one's got a gradient of 2 and y-intercept of minus 7. And hopefully they're looking pretty good in being parallel lines there. You can see that they're never going to touch, and so that is why we end up with that no real solution. I hope that